Okay, let's see what we can do here. Yeah, I'm still so new at this. I'm not even sure if I have any of my audio settings right. Let's see. Can I at least hear myself through this? Okay, yeah, I think this is good. Well, I had huge ambitions to do a lot more on today's stream, but this is probably just going to be a quick experimental thing. I might not even save it. Okay. Let's turn you down even a little bit more. Okay, so this is new for me. I mean, I think I mentioned in my last stream that I've streamed before, but nothing like this, and certainly not live programming. But just thinking about little toy projects that I could build to um, sort of just act almost as fodder for some of these early streams, just so I can, because for me it's mostly about just the muscle memory of um, starting little toy projects from scratch. I don't do that very often, and I need to, but also like just getting my feet wet with streaming again. Um, so pretty low stakes. The idea I have a few ideas for things to build that might be interesting. For now, the one that I wanted to keep it fairly low scope, somewhat well understood, um, and something that is close to my particular like technical domain. So, um, what I was thinking was a uh, effectively implementing a route lookup system for IPv4 and IPv6 network addresses, and sort of doing the typical longest prefix match thing. But I wanted to add a little twist just because I wanted to add the ability to route also by port ranges. So where you might say, I just want to pick the route that it includes the longest prefix that matches the address that I'm looking up. I want to also include the requirement that the port ranges, and there could be multiple, that are associated with that route should also match. And that's sort of like a binary yes or no. It should match or should not. Now, the interesting question that you have to ask if you do that is like, what should the longest prefix match behavior be like? Like, you could argue that you should um, preserve the longest prefix match functionality at any cost, which would mean that you do the LPM match first, and then if the port isn't in one of the ranges for that route, then you simply drop it. That doesn't match anything. What I want to do instead, and maybe I'll make this like sort of configurable. That might be a good thing to add, but just optionally, what I want to do instead is effectively do a walk back where you say like, give me the longest prefix, but also keep track of like the ancestors that had routing entries. So like if I encounter shorter prefixes that do match along the way, I'll sort of keep a minimal stack of those. I think this is probably worth doing like a visual, or maybe just like a write up of like my design first. But I don't have that in front of me, so I'm probably just going to start with some of the simpler stuff. Like I said, today's stream is going to be very short. I had ambitions to start this like 2 hours ago, and just it didn't work out. Like I said, I'm still getting used to this. But I suppose next stream what I'll do is I'll just do a quick overview of like uh, what the overall design will be. But for now, I think today I'll just be satisfied with getting some of the basic types defined, and maybe like a beginning of the actual like Patricia tree implementation. But more than likely, I'll just be laying out some structs today. Um, tomorrow, or even not necessarily tomorrow, but the next stream I do, I'll try to be a little bit more prepared for this side of things instead of just screwing around with OBS all day, all morning. So let's see. I think I can switch this now. Yes. This is what I was spending all morning doing, screwing around with layouts and things like that. And as you can see, it's still totally not perfect. But anyway, starting from scratch, haven't done anything here. I haven't even run the cargo init, so this is going to be in Rust. Another thing I just don't do very often. Like, I've written Rust professionally for a little over 4 years, and you know, every once in a while I'll bootstrap little toy projects. But to be honest, like, my work mostly is quite varied. It's not necessarily just Rust. It's not necessarily. It's literally not just Rust. So it's like the frequency with which I make brand new things in Rust is not like just natively built into that. So like, I'll do Advent of Code. I didn't do it this most recent year, but I've done it the 2 years prior. And that's kind of fun. But that has limits. Now, every once in a while, this lo-fi generator gets into some weird syncopations, and it makes me think I have like a feedback loop somewhere, which I think I'm predisposed to believing because of how painful it was to set up the audio for this. Man, that is still a lot louder than I want. I may just kill that entirely if I keep getting distracted by it. I think it was just that one song. I think it's happened before. Okay, so it looks like stream health's okay. A couple dropped frames a little bit ago. Yeah, CPU's up there, but that's not that weird. I don't think I'm doing anything crazy. I wonder if BTOP itself is actually causing issues. Yeah, I might just kill that. Well, it's fine for now. We'll see if we cause any additional dropped frames. I think overall things are going okay. All right, so let's see. I'm gonna init this, and then so LPPM I'm just naming its heart, but I was just thinking longest prefix and port match. That's kind of the idea. So let's see. We get no README. No, not right now. Oops. I could have just done this straight up, but that's okay. LPPM. Longest prefix import match. Let's do our capitalization correctly. I don't really have continuation, like auto cutoff in Markdown. Huh. I'll have to do that. I didn't think I had missed that. So let's see. I'm gonna actually. So I do have like a very rough, like Markdown file outside of this that I was just jotting down a few thoughts, but it's real informal and messy. I don't want to like bring all of that garbage into here, so I'll just be copying some of that in here clean. Let's see. Let's just do an H2 for design, and I'll just add to this later if I want to. The idea generally is it's a patricia tree. Patricia tree, either way. Um, and if you don't know what a patricia tree is, it's a radix tree. I'll get to that in a second, but it's a radix tree in base 2. It's sort of just like a specific radix tree. But a radix tree in general, regardless of sort of like what base you're working on, is how can I explain this? It's been a while since I actually like thought about how to define it, but it's a tree structure, obviously, and it's a binary tree. It's a binary tree structure. The idea is that you encode effectively bit level information about your input into the tree itself. So it maps really nicely. Specifically, patricia trees map very nicely into IPv4, IPv6 addresses, network addresses, right? Because obviously we know if you're used to dealing with network addresses, you're accustomed to thinking of them at the bit level, especially prefixes with like CIDR notation and whatnot. So the idea is that if you want to insert a particular address into a tree, you effectively start with the first bit and you say, is this a 0 or 1? And if it's a 0, then you go to the left. And if it's a 1, you go to the right. And then you go to the next bit, and that gives you the next layer of depth. And so as a result, as you might imagine, a tree with that's designed to store IPv4 addresses could be up to 32 nodes deep, have a depth of 32. And then, of course, the width depends entirely on like the input. So like what kinds of addresses or what kinds of addresses that you're storing in it. Now, the cool thing about the using this for longest prefix matching is it's kind of built in. You actually don't even really need to like store the prefix length anywhere, right? Like if you have like a series of routes, you just basically walk the bits from most significant to least significant, and then you just end at the prefix length. So you say like if I have a /24, I'll make sure that the first 24 bits of you sort of mask by virtue of ending at the 24th bit, because you almost certainly, you wouldn't want to, I'm just trying to think, it's been a while since I implemented this myself, but you certainly wouldn't want to implement, you wouldn't want to just encode all of the zeros. You'd want to end at the prefix length because that's where the actual route is, so you don't want to terminate there. Anyway, I'm talking with my mouth too much. I should probably just write most of this down. But that's the idea. Patricia tree is the data structure. So let's call it a traditional patricia tree for storing encode. Let's see. Each separate v4 and v6 trees for now. The reason I want to do this is because the depth is different. So there's two ways you could do this. You could encode, like you could just commit to a single tree of maximum depth 128 because it's 128 bits in a v6 address. But you might run into issues. Well, at a minimum, you'll be sort of committing to, I mean, there's things you can do to optimize, of course, but there is a way to use one tree for both. It just comes with trade-offs that I don't want to deal with at the moment. And it'll be trivial to collapse them later because I'm going to build the v6 tree as well. And so if later on I want to have a single tree, then I just delete the v4 implementation and just reuse the v6 tree with whatever mechanism I need to be able to differentiate between the two at lookup time. So yeah. The other thing I wanted to cover is, simplicity. The other one I wanted to cover is port ranges. Basically, each route will come with a series of port ranges. And where was I going with that? Each route will come with a series of port ranges, and that must match an incoming packet. Well, let's just call it a lookup. However we want to look that up. That must match an incoming lookup. This means that LPM takes place first, but the longest prefix must also match one of but the port in the lookup request must match one of that prefix's port ranges. If it does not, fall back. I should have a requirements section, I think. That's what I should do. Yeah, I'm mixing things up a little bit. Allow, we'll just say fast lookup of a routing directive given an IPv4, IPv6 address, a layer 4 port. Because TCP or UDP doesn't really matter. So layer 4 port. Of course, we could, you know what we could do? Well, we'll add that later. I'll just add that to like the to-dos. But I was just thinking like we could also differentiate by TCP or UDP. That doesn't add too much to the design, because we got LPM first, which is again O of 32 at most for v4, so that's pretty constant. This is for lookup. Like insertion's different, but for lookup it's O of 32, but then plus a binary search for the port lookup. So this would be effectively another plus O of 1, because we're effectively doing just a Boolean check. But I'll note that later. That's again getting into the implementation. To-dos. What did I just say? Layer 4. Oh, right. TCP or UDP filtering, I guess. Or both. I suppose you could do both, right? Where you say like I don't care. Like if you care, you could make it just an enum of like TCP or UDP or both, and then yeah, like you just do sort of like a check of like if it's both, then don't worry about it. If it's one of the two, then make sure it matches. But again, it's going to be constant time. So allow fast lookup of a routing directive given an IPv4, IPv6 address, and an L4 port. Lookup should behave like typical longest prefix match, but also must match one of the port ranges in a route. If the longest prefix is port ranges do not include the L4 port, the second longest matching prefix should be considered, and so on and so forth. So this is the sort of like shorter prefix fallback. I'll just leave this out for now. Where did I put you? Oops. Where did you go? Oh, right. Yeah. Still getting used to that too. Okay. Okay, and then what do I do this? So let's cut this out actually, because that's a requirement. Sure. Each route node should have an optional field indicating if a route exists. Yep, it's because not every node will have an actual route. It might be just a pathway to a route. The other thing I wanted to capture is also the route should include port ranges. And we should maintain a stack of ancestors that had routes, so we can walk back to find matching port range. All right, this isn't even really designed. These are mostly just sort of like loose thoughts. I think this is probably fine for now. Pretty much anything else that I was going to sort of get into really just gets into the implementation anyway, so I don't think it's a huge deal. I think probably what I want to do now is switch over to, oh, well, actually, no, never mind. I don't think I want to do that. Yeah, that's fine. Okay. All right. Yeah, unfortunately, like I said, I'm running out of time this morning, so I might have to cut this short. Let's see if we can get some structs in place at the very least. Oops. All right. So, oops. Yeah. Let's see. We want that. Yeah. Yeah, I just have a list of structs I want to define. Okay, let's start with something that we know we need. Port range is probably going to be the simplest one. We'll do, yeah, let's just do low, high. And think that's fine for now. We'll probably need something, not a field, but maybe a method to help with the binary search later. But let's deal with that later. Oh, that's the other thing I wanted to note is just a real quick back of the napkin math on time complexity. Let's see. The binary the tree lookup is going to be constant. So tree lookup is O of 32, and then really the only thing we would need to do is, I'm just wondering about the fallback, but the port range lookup is going to be just log n. It's binary search. But again, I'm trying to think of what would happen. Port range lookup is O log n. Yeah. But then, like I said, as I say, the worst case time complexity would be if, and of course it kind of depends on the number of n, but I mean it's log n, so it doesn't matter too much. But I'm just saying, like, if we do the walk back on the ancestors, where we say, okay, the longest prefix didn't match, so we need to walk back this stack that we've been keeping track of, these ancestors, that would be worst case, effectively like 32 times log n. So it's probably worth capturing that times worst case scenario. Something like this. Yeah, I'm just thinking like that has to happen each time. And that's, again, this is like a really worst case scenario where like every node has a route and none of them match. So O of 32 plus O of 32 times log n, something like that. Of course, this changes a little bit. It might change. This is absolute worst case. Realistic estimate. Yeah, realistic estimate is O 32 plus log n. Because that's almost certainly what it's going to be. Might have some additional complexity if we do protocol matching too, but unlikely. Yeah. Oops. Okay. Captured that. Okay, so we've got the port range. What's the next thing? Oh, the other thing is just like the action. I'm going to keep this simple for now. Probably just like an enum of like, I don't know, drop or allow or something like that. We can always add to it if we want to do something. The routing directive is not really the important part, so I'm not too terribly worried about it. So, yeah. So enum action, and we'll just do drop and allow. What's the next thing? Route entry. So action, we want to do the action there, and then we'll have to have the sorted port range because that is what we need for the binary search. So let's do that. So tree, and we'll call this action, and then we will say port ranges. We'll call this a vec of port range. Sorted port ranges in binary search on lookup. And then we'll definitely want to do probably, I mean, I don't have to do this now. Let's say route entry. Yeah, well. Yeah. Port ranges, and we'll do a vec of port range. I could imagine that we'd want to I would imagine that we would want to do something like well, sorry, incomplete thought. We want to make sure this is sorted, so we have to enforce that somewhere. I'm assuming that for now we would just assume that it's sorted outside, but at some point we'll want to make that simpler, where we either sort it here and don't really care how it comes to us. We'll sort it on ingest, which I think makes sense because we'd have to sort it outside anyway. So I think it just makes sense to put it in, make sure it's in like the data structure. And again, like the thinking is that this would be in a library, and so you wouldn't even really be able to construct a route entry yourself. You would just call either the constructor or probably some even higher level function that doesn't even expose this to you. So it doesn't really matter too much, I wouldn't expect. But we'll get to that later. I'm sort of skipping ahead because I don't even know how I want to expose this. For now, I would say let's just keep it simple, and we will do, let's just actually, yeah, real simple. So allow, and then port ranges, we'll just do, yeah, we'll just pass that in. Sure, yes, that's fine. So that's there, but I do want to capture what I was just talking about. Need to enforce sorting here probably, and also need to ensure port ranges do not overlap. Yeah, that is definitely what you want. But again, we'll do that later. We'll just assume that they're not overlapping for now. Let's see, the other, so this is sort of where we bring things together. We need the node now. So struct node, this is where we actually store not only the route entry, but also like the left and right decision. Now, well, I'll just say route entry. Oh, this needs to be an option. Because not every node will have a route. And then that gets into the left and right. So I am planning on making this, and this is probably something I should put in the design, sort of like memory allocation up front based on, I suppose, yeah, so 2 times, so into heap allocated vec, not that there's a difference, not that there's a not heap allocated vec, and so let's just call it a vec. Based on number of prefixes. So when we build the tree, we'll have to have already read in the list of routes, which presumably some other part of our system will do that first. So we'll have that length, and then we will want to allocate a yeah, let me write this a different way actually. So nodes will be stored in a vec and referenced by index. And I'll just refer to this as arena style because we allocated up front based on number of prefixes being added. And it'll actually be 2 times num prefixes because every prefix can add at most 2 nodes. Obviously, there'll be plenty of reuse, so this is again another one of those overestimations. But we can tweak that later if we want. And this really shouldn't be that much memory anyway. Obviously, it will waste some memory because, like I said, you'll never hit this. You'll never hit 2 times num prefixes. You'd have to add literally every. You'd have to add effectively every individual /32 or /128, which would be kind of crazy. So this will definitely be an overestimation of that. But we can play with that later. I think for now it's better to just guarantee that there's enough space so that we do a single allocation up front. But maybe I can add it to do later to sort of be a little bit more conservative on this. You just have to sort of find the sweet spot because if you start to fragment memory, the lookup speeds can get slower. Just depends. Consider just adding some to-dos for later. Consider lower. More conservative memory allocation. Okay. Yeah. Okay, so kicking off now where I left off. So what that means is that every node will need to have a left and a right. But because of our strategy, it'll be quite simple. We don't have to do anything with pointers or references or anything like that. Let's do option. Yep, because again, they may not have one. So we'll do just a usize for this, because that's what we'll be using for the index into the vec, and write option usize. And I'll just add some comments here to make it more obvious. So there is a 0 in the init. There is a 0 node ahead of us. There is a 1 node ahead of us. Something like that. And then, yeah, so this is it. This is all we need. And then we just need to do our tree. We can put it all together. So struct tree. We'll do the... I mean, basically, we just need vec of nodes. But is that it? Well, you need the root. You need the root too. We could always, I mean, by convention, we could just make sure that the root is always stored at index 0, which it will be anyway. But we'll just add this field just to make sure that we're tracking it somehow if we want. Size. I guess yeah, I was thinking option. I mean, yeah, I just don't. It's like why would you create a tree? Yeah, I don't like that. I don't want that. It was my original plan to do it this way, but I'm changing my mind. So, that power. Root node is always available at index 0, so that's where we'll start all the time, no matter what. And that means we can get rid of this. And it also means that when we actually set this thing up, we can do a little bit more to ensure that that convention is respected. So I think that's what I want to do for later. So I'm just looking ahead a little bit at my prediction of what I might want to do later. And I really should have incorporated these into the notes. But that's okay. Anyway, let's just do our constructor for this, and then I'll probably need to call it. I'll do fn new, and we will want the list of routes, but I'll add that here in a second. And then we'll say, did I not use self up here? Probably not, right? That's a bad habit I have. Let's just do that. Oops. Whoop, yeah. And then, yeah. So we want to do, we do kind of need the prefixes. So let's say, I could bring in the IPnet crate because that just has prefixes built in, but I don't know if I want to do that yet. Let's just say, for now, we'll add our own. We'll add our own prefix. Yeah. IPv4 prefix. Because right now I just need the IPv4 address and the prefix length, and I can build from there. So adder equals IPv. Oh, did I bring that in? Probably not. Nope, not even bringing anything in at the moment. Use about. I always get the casing wrong. So yeah, IPv4 adder. Probably, I mean, obviously later on I'll want to probably just convert that to just an IP adder instead and just do the matching there. But it's on the tree specifically. So again, like this is all temporary, so I don't care. I could just make this v4 specific at the moment. Should be easy to fix later. So we'll just say IPv4 adder. And plen is call it a U8 if we really wanted to. Just do U size, doesn't really matter. And then, yeah, sure. For this, we will then do, here, right, so prefixes. This is what I was wanting to do. And this will be a vec of IPv4 prefix. And then we will say let nodes equals, and then we'll want to do vec with capacity. This is the important part, so we don't do crazy allocations all over the place. Prefixes.len times 2. Sure. And let's explicitly declare this type while we're here. Vec of node And then that way we can do tree. Okay. Yeah, new is never used. Yeah, that makes sense. Oh, and did I probably, yeah. Okay. Oops. Yeah, that's fine. Okay. I think I am satisfied with that. Probably want to do yeah. Well, yeah. I don't want to get. I don't want to get into the actual insertion into the tree, but we can end on let's just do the let's just do the alloc node, like allocating a new node. So we don't have to actually insert it to the tree yet, but we could just add it to the vec. Yeah. Alloc node, and this will be oops. So we need a mutable reference to self because we'll be mutating at that field, and then we'll say node. Then we'll say okay, self.nodes.push node. And then, yeah. Oh, the one thing I wanted to get is then we can then return. I want to return the actual index. So usize because we'll want to use that index to store in the tree in the left or the right element. So we'll do self.nodes.len -1. Okay. I think that's fine for now. Given my hectic morning, I think I'm satisfied with that. This is a nice foundation to build on later. Okay. I didn't even send any notices about this out, just because I'm just trying to make sure it's good first. But in case you're watching, thank you for watching. And yeah, hope to see you on the next one. Thank you.